Okay, thanks.
Hello, sir. Why tutorial sessions were stopped, sir? I saw only a couple of sessions at the beginning, later on discontinued.
So is it, I was under the impression that the TAs were unwell for 2 or 3 weeks. Okay, the TA was unwell. I was under the impression that it resumed.
No. Actually, I've been following it. I was, in fact, the mails have been coming, but the sessions are not scheduled. Yeah.
Okay, so let me find out. Okay, thank you for bringing that to my attention. Yeah, okay, so I think we are live and we can discuss any technical doubts you may have from your tutorials or assignments or otherwise.
Sir, a general observation and maybe a suggestion is required from you. See, I am a faculty member. In fact, I'm more of a pseudo faculty in the sense I was an IT professional for 30 years. Now I wanted to keep my brain active and I'm doing courses in electrical engineering. And this is the first time I took this course and probability for electrical engineering. Though I had a background right in the way back in my college days, but that was more of applied probability, as you said.
Correct.
Right, computing expectations, computing that correlations, etc., based on well-defined formulae. In fact, I have been sincerely following your rigor of the analysis, but this is my personal observation. But somewhere I'm getting disconnected in the sense that it is becoming abstract. So is there any way that we can put example first and slowly get into abstraction rather than putting the statement then the statement then?
True. So I would teach undergraduate students exactly as you say. This is a graduate level course meant for PhD students. Which sort of assumes that they're already familiar with the basic calculations and all that, right? So what you said is exactly how I would teach the undergrad version of the probability course. This was the recording that you see online is the PhD or graduate student version of the course, postgraduate version.
Yeah, I understand. That's perfectly, it's okay. Because it's said for electrical engineers, then I said it will be more of applied thing rather than with the mathematical rigor. Okay, but I saw one course. When I looked at it, I think taught by Aravind sir or something, IIT Madras. Same name.
Aravind, yeah. So that is the undergraduate course. So if you want more undergraduate treatment with many more examples and less abstract theory and all that, the course taught by Andrew and Aravind is probably more suitable.
Okay, sir. Okay, I understand. I'll do both. Thank you, sir.
Yeah, thank you.
Sir, we have a question in the chat.
Yeah, we have a question in the chat. Okay. Hang on. We have a question in the chat. Is 2 power n equal to r? Balasantosh. Hi, Balasantosh. Yeah, the cardinality of 2 power n is in fact turns out to be equal to the cardinality of the reals. So the reason being that you can easily map. So if you take, 2 power n, are you able to see the screen?
Yes.
So if you take 2 power natural numbers, which is the set of all subsets of natural numbers, right? So each element of 2 power n is some subset of natural numbers. Correct?
Yeah.
So for each subset A of n, right? We can associate a binary string, infinite binary string. Right? So if A takes, so the point is that if, let's say, A takes, let's say, only odd numbers, right? Then the binary string will be
0, 1, 0,
1, 0, 1, 0, right?
Yeah.
1 denotes whether I take that particular number in my subset or not. 0 means I don't take. Okay. 1 means I take. So if you give me any subset of natural numbers, it will have some natural numbers, and will not have some other natural numbers. So for whatever natural number is contained, you put a 1, which is not contained, you put a 0.
Okay.
Correct. So 2 power n is in bijection with, and vice versa, actually, I should write, and vice versa. So this implies 2 power n is equicardinal with what? Infinite binary strings, right?
Yeah.
That's all that we need. That's all, right? Which is equicardinal with R, because it's like a binary representation, right?
Okay.
That is all there is to it. There was another question in the, I think in the online thing, that from what about set of all functions from n to n? Is it countable or uncountable? Bala Santosh Ganesh, is that you?
Yes.
Bala Santosh Ganesh. Okay. So you had a question about, so this is number 1. If you had number 2, which is the set of all f from n to n, right?
Yes.
It is also uncountable. Okay. So this is called n power n. Okay. The notation for this is n power n. Okay. For each natural number, you associate a natural number.
Yeah.
Okay. So in the previous case, for each natural number, we assigned 1 or 0. Correct?
Hello?
Hello, you there?
Can you hear me?
Yeah. Loud and clear.
Oh, okay. Fine. I thought I was on mute.
Yeah, so for each natural, f from n to n is for each natural number, you assign a unique natural number, right?
Okay.
That's a bigger set of, that's at least as big a set as assigning for each natural number 0 or 1, which is our previous case.
Okay.
Is that, you understand that? So in the previous case, for each natural number, I just said yes or no, 1 or 0 in my subset.
Okay.
Correct? Now for each natural number, I'm assigning a natural number.
Okay.
So which is at least as big, right?
Yeah.
Yeah, so it's clear that the previous set is uncountable, this is also uncountable. It turns out that this has the same cardinality as 2 power n, but that is beyond our scope. Okay.
Oh, okay.
I'll just say it's also uncountable.
Okay.
Turns out that n power n and 2 power n have the same cardinality as reals. Okay.
But n squared is countable, right? N squared, n cubed.
N square is countable. Any Cartesian product of countable set with is countable.
But n power n is not countable.
N power n is uncountable. N power, just like 2 power n is uncountable.
Okay.
Hello. Good morning, sir.
Good morning.
I am Sagar.
Hi, Sagar.
Yes, sir. I had some confusion regarding this point-wise convergence and the almost sure convergence thing. I'm not able to visualize or find where to read these materials. Notes it is very brief, and I'm not able to understand like what is the difference and which one implies which, and if other how we can go from one definition to other definition.
One definition to another definition of
And does this point-wise convergence implies almost square convergence?
point-wise convergence. Yeah, so you're talking about point-wise convergence. Wise convergence. Right, so point-wise convergence means you have xn of omega converging to x of omega.
Yes.
All omega and omega. Right?
Yes, sir.
Almost sure convergence is a little bit weaker. Okay, so we are just demanding that you collect all the omegas for which xn of omega converges to x of omega. Okay.
Yeah. And their
We are
probability
just
is 1.
demanding that the probability of that is equal to 1.
Yes. So
Okay.
when does the almost sure convergence can imply this thing? Point-wise convergence.
So
Is there any
generally almost sure convergence is slightly weaker, right? There may be omegas of 0 probability where this convergence does not take place.
Yes, sir.
Correct?
Yes, yes.
There may be 1 or 2 points where this convergence doesn't take place, and those few points where this convergence take place may have probability 0.
Okay.
In that case, you have almost sure convergence, but not point-wise convergence.
Also, sir, we talked about convergence in distribution. Like this distribution can be for 2 different random variables. Like the distribution for 2 random variables can be same. So in that context, like why do we read about this convergence in distribution? Like I am not able to get idea why. What information this
Convergence in distribution. See, convergence in distribution does not mean that the random variables are getting close. See, almost sure convergence means that the xn sequence is getting close to x, right?
Yes.
For almost all omega, right?
Yes, sir.
But in the convergence in distribution, the random variables are not getting close. It's only the marginal distributions are getting close. So you take xn, right? I say PDF is fxn of x. Right? So you just look at the marginal distribution of xn.
Yes, sir.
Right. So this is the CDF of xn. Okay.
Hmm.
So for convergence and distribution, we just demand that fxn of x converges to fx of x. It is the limiting distribution for all x where fx is continuous. Okay.
Okay.
So it's just that the distributions, the marginal distributions of the xn sequence is getting close to the distribution of x. It's not the case that the xn sequence is actually getting close to x.
Okay, so where do we need this type of
for example, right? So an example in central limit theorem. Have you come to central limit theorem?
I'm reading this week.
Yeah. So example in central limit theorem, this is the most famous example of convergence and distribution. Yes, the point is, so you take Sn is equal to sum over xi, right? Xi being IIT.
Yes.
With mean, mu, and variance. Correct?
Yes, sir.
Now, you'll take, let's say, Zn as Sn minus n mu by sigma root n. You're subtracting the mean of Sn, scaling by root n. Right?
Yes, sir.
So the CLT says
normal distribution with
Zn converges to Z, where Z is normally
normal.
distributed, right? A
Yes.
standard normal. Correct. See, my
Yes,
point is that if you keep doing this, so you keep generating exercise, compute Sn over minus n mu by sigma root n, the distribution of that will get close to a Gaussian.
Yes, sir.
But it doesn't mean that Zn is getting close to some Z. See, my point is, let us say you generate, see, then it's very different from the law of large numbers. So let me intuitively tell you what the difference is. Okay, listen carefully.
Yes,
So
sir.
let's say you generate 10,000 samples of a random variable, IID. Okay, and you
Yes,
take the sample average, Sn over n.
Yes, sir.
Okay, and let's say your friend also does that. He generates some other 10,000 samples from the same distribution. Okay, and takes Sn over n. All right.
Yes, sir.
So your samples are different, his samples are different. Okay, you have a sample average of 10,000 random variables. From the same distribution, your friend draws independent samples and calculates the sample average. Correct?
Yes, sir.
Now, the point is that your average and his average will not be exactly the same, but they will be close.
Yes.
Correct? And suppose this 10,000 becomes 1 lakh or 1 million. Then what will happen? Your average of Sn over n will be even closer to your friend's average of Sn over n. Right?
Yes, yes.
And no matter how many people do this, even if everybody in your class were to do Sn over n with different samples, right? Almost all of them, almost surely, these averages will be going to mu, right?
Yes.
Is that clear?
Yes, yes.
But now suppose you do not Sn over n, but Sn minus n mu by sigma root n.
Yes.
And your friend also does that. Okay. Will your two values be close?
No, how will we say that?
They will not be close. That is my point. Okay. So you will, so Sn over n will be very close for everybody. That you agree, right?
Yes.
So that is what law of large number says. The Sn over n sequence actually converges to mu as n becomes large.
Yes.
Whereas the Zn sequence, which is the centralized Sn minus n mu over sigma root n. This, if you take each of you takes 10,000 samples and computes Zn, right?
Yes.
They will not at all be close. Okay. So these Zns are not converging. Your
Okay.
Zn can be very different from your friend's Zn, and if all your classmates compute Zn, okay, they will not be close to each other.
So, sir, here, which is stronger, sir? Is it distribution convergence or the point-wise, what you said earlier? Which is stronger?
Point-wise. Point-wise.
So point-wise is the most strongest. You can see my lecture on these things. How the convergence hierarchy works. You can see the weakest is convergence in distribution.
Okay, sir.
So let me finish my point. I was saying that all of you generate this Sn minus n mu by sigma root n, right?
Yes, sir.
You try doing this. You can actually do this. If you know Python or MATLAB, you can do this, right? You can do 10,000 samples. So you can ask your friends to do 10,000 samples. Take Sn minus n mu by sigma root n. Okay.
Yes, sir.
Your value of Zn will be very different can be quite different. They will not at all be close. Even if n becomes 1 million, 2 million, they will not be close. Okay. But here is this important point. If you take your value of Zn and your friends, all your classmates have different values of Zn, they will not be close, right? You plot the histogram of this, of all your Zn values.
That will come as normal distribution. Normal distribution.
That will be a normal distribution.
Yeah.
Okay, it's not that your values are close, but the CDF of Zn, right, it will be close to a normal.
Okay.
Okay.
Yes, sir.
That is what it means. Is that
Yes,
clear?
Yes,
That
sir.
is the qualitative difference between law of large numbers, which is almost sure convergence, and central limit theorem, which is convergence in distribution.
Okay.
Law of large numbers means, or generally almost sure convergence means, that the sequence of random variables itself gets close to the desired limit.
Yes.
Right? The convergence in distribution, the sequence of random variable need not get close to anything. It's just that their
Distribution.
marginal distribution is converging to, in this case, in the central limit theorem case, a Gaussian.
Yes, sir. Now it's clear.
Clear?
Yes, sir. Sir, when we were talking about transformation of random variables,
Mm-hmm.
when we are doing this transformation, the functions which we are taking for the random variable,
Mm-hmm.
we are like for monotone type of function, decreasing or increasing. I understood like it will be like we can find the inverse of that in sigma like sigma event space, and then we are able to do this calculation. It will become the functional inverse, and it get easy to do the calculation in that CDF approach. But when we don't have that function monotone decreasing or increasing, it is very random type of function. Then what we have to do, like it is increasing and decreasing sometime. Then how to deal with those type of functions? Just in a hypothetical condition, I'm asking. Normally, when we have monotone increasing decreasing function, we can just take functional inverse, and we can go with the CDF approach and
Yeah, you can go. See, I think you can. This Jacobian formula depends on monotonicity.
Yeah,
Right?
it's injective. No, we have to verify it is
Yeah, that
injective.
is. It's a very special case. Otherwise, it's better to do from first principles.
Yeah, CDF that work very easily when we have monotonicity or injectivity.
Yeah, if x square, for example, right? If you have example, I think I did something like this. So if f of x is x square, let's say,
Yes,
right?
sir.
X is normal 0 sigma square or something like that, right?
Yes.
Say y is f of big X, right? You
Yes,
want
sir.
to calculate. So the f of x is not monotonic. It's decreasing and then increasing, right?
Yeah. Yeah.
So if you want to look at the probability that y is less than or equal to little,
But here we can break this into
you have to do it from first principles. That's all, right? Here
yes.
if you write this probability that x square is less than or equal to little y, which is the probability that
Y
minus
is in between
y
minus. Yeah,
y. This you can proceed, right? This you can easily write in terms of Q function.
yeah, yeah.
Right? So you have to, do it from first principles.
So while applying Jacobian, I have seen like most of the places it is not verified that this is the function is injective or not. So
Yeah,
is
that's
it
wrong. I think I mentioned this in the lecture. That Jacobian approach may not always work.
yeah, even Grimit also they are not verifying, checking it. They just apply in the problems.
But I think Grimmett will not make such mistakes, but they would have said somewhere, if you look at it.
Initially, they have said it when defining it, but when they are solving problems, they are not saying. I'm just telling that when we solve these problems, do we have to show that it's injective, or we can directly do these things in anywhere?
I would recommend that you check every time, right? Actually, I don't like using the Jacobian formula. I always use first principles.
Okay.
That way you can never go wrong.
Yes, sir. Sir, one more hypothetical question. Like in a scenario when we are having functions where they are different random variables, and we only know the distribution of those random variables, and we want like what we call joint distribution or something of like the function we got, we want the distribution of that function. Is there how to proceed in that sense? Like just I have some variables which have distributions, but a final function which I got, I want the distribution of that to do the analysis.
Okay, so if you have dependent random variables, you cannot do it in general, right?
Yes. For independent, we can do.
Independent, you may be able to do. See, if you are given the joint distributions of a bunch of x and y or something like that,
then we can do all those
then
things.
You can do. Because with marginals, you can't find.
So in real life, how do we model those things when we have these scenarios? We can have these scenarios where we know this parameter have this distribution, this has this distribution, and all these things manifest into some other operation where they are being used.
So, yeah, so you can have a function of two random variables, let's say,
yes,
g of x comma y. So if you are given only the marginal of x and the marginal of y,
yes,
you cannot find the distribution of x g of xy. Generally not possible.
So what else information we need for in that
If you
scenario?
have, if you know something, if you know the joint distribution, sure. That is the short answer is you should know the joint distribution.
But we don't know all the time. In real
Yeah,
life,
we
can
don't
we
know. We
modify?
don't know. If you know independence, you can calculate. Otherwise, you cannot. In general, you cannot. You can make some approximation saying they are independent or whatever, right? In real life, if variables are correlated, they are dependent.
Yes, sir.
Calculate the distribution of g of xy given the distribution of x and the distribution of y alone. Given the joint distribution, you can do it.
So how to proceed in those scenarios? Like if we have a problem, like if we are solving some research problem and then we get these scenarios,
You have to make some assumption, or you have to.
there is like we can't get a perfect model without assuming some
No,
about.
I don't think you can get a perfect. No, you cannot get a perfect function in general because x and y could be arbitrarily dependent.
Okay.
So just given the distribution of x and the distribution of y, you cannot find the distribution of g of xy. You can't even get close in general.
Yes, sir. I was reading about this. Like I am taking doubts. If other has, they can ask. I have a lot more doubts. Until then, if anyone has doubt, they can ask. Otherwise, I will continue asking.
I think you can also, there is a request for making a 12-week course into 24-week course. I don't think there is such thing as a 24-week course, Bal Santosh. I think the way to do it is to start early, start watching the lectures early, right? NPTEL does not even have a concept of a 24-week course. Okay, that is just a very long course. Okay. Yeah, so any other doubts you were saying?
Sir, this regarding convergence, the word like probabilistic convergence I heard, is it the same as the distribution convergence?
Probabilistic convergence, I don't know what it means. So there is convergence almost surely, there is convergence in probability.
Convergence in probability. That means it implies a distributed distribution convergence.
Well, convergence in probability, let me just tell you what it means. Let me, where was I? This is convergence in distribution, right? I'll tell you what convergence in probability means. So xn converges to x in probability I dot p. This means that limit n tending to infinity, probability that xn minus x greater than epsilon goes to 0 for all epsilon. Okay. Just this means that the difference between xn and x becomes very small as n becomes large.
Yes, it is only in the limit, sir, not absolute, right? Limit.
Yeah, so for large enough n, xn and x are very close.
Very close.
Right?
Isn't it means,
high probability. That's what convergence probability means.
Sir, I had to say, like, isn't it means that in event space, whichever omega we are getting because of this random variable, this is a random variable xn mod this one is having the probability measure equal to 0.
So this sits between almost sure and the convergence in distribution. So this is weaker than almost sure convergence. Okay. Almost sure the convergence implies convergence in probability. But convergence in probability does not imply almost sure convergence. Okay. Because xn minus x can get very close with high probability, but the sequence itself need not converge. Okay, so I think if you watch my lectures, you would have seen all these examples. Okay, I give examples of this. See, convergence almost surely implies convergence in probability, but this way is not true. Okay, so for example, if you take xn is equal to 1 with probability 1 by n, equal to 0 with probability 1 minus 1 by n. Okay. So if you have, does xn tends to 0 in probability? Question mark. What do you think?
Yeah, at 1 by n, it is only 1, and it is very one thing. So I think it should go to 0 now.
Yeah, so probability xn greater than epsilon, right, is what? So absolute value of xn minus x here is 0, right?
Yeah.
So probability xn greater than epsilon is simply the probability that xn equal to 1.
Yes.
Right? So that should be how much?
1 by n, and when n
1
goes
by
to
n.
t.
Right? So and n goes to, so this goes to 0 as n goes to infinity. Right?
Yes, sir.
So answer is yes. Right?
Yes, sir.
Now if you look at does xn go to 0 almost surely? Let's say xn's are independent. I didn't say that earlier. So xn does not, here the answer is no. Okay. To see why this is the case, you have to go to BC lemma. Remember BC lemma?
Yeah, Borel continuum.
You have to go back to BC lemma. Okay, and then see. Okay. So here the issue is that for any xn, right, the probability that xn is 1, the xn that xn fc is epsilon is very small. It's 1 by n. But if you look at any n, there are infinitely many ones. Okay, beyond any n. So which means the sequence doesn't converge. There are occasionally some ones keep popping off. Okay, according to BBC lemma, you can go check this.
Yes, sir.
Okay, so convergence in probability is weaker than convergence almost surely. Strictly weaker.
So, like, could I proceed with my questions then?
Yes.
Yes, sir. Like, when we were like discussing about conditional expectation, we wrote this expectation in a like in a conditional like probability and distribution sense.
Mm-hmm.
But when I was reading books and my course material, which I'm taking here in my college, we also studied conditional expectation in a like axiomatic way, where we have 3 axioms with like conditional expectation given an event space we discussed. So I understood like here we have some what we call axioms and some conditions we verify and we say this is conditional distribution.
Mm-hmm.
But I didn't get a like link why we jump from those 2 definition and how why it was required to have that thing from there to here in this particular thing.
So why we are asking? So why go from something like this?
Yeah, to
Or
the sigma.
Something like x given some event
Sigma
a,
y.
right?
Yeah.
Expectation of x given f.
Yes, sir. Yeah, that's what my doubt is.
Right. Short answer is this is more general.
Yes, sir.
Okay. See, expectation, let's say you're looking at expectation of x given y. Right? How do you calculate it? So you calculate it as, let's say, if y is discrete.
Yes, sir. Summation of x.
You will say it's expectation of, you take expectation of x given y is equal to little y.
Yes, sir.
Right? You call it p of little y.
Yes, sir.
Right? Then you, then phi of y, big Y, is expectation of xy. Right? That's a random variable.
Yes,
Correct?
sir.
It's a random variable. Now, what if y is some crazy random variable, some bizarre random variable, right? Some mixture or singular, etc. Right?
Yes, sir.
Then you don't have this.
Yeah.
So if y is discrete, you will calculate it as sum over xi, I probability p of x is equal to little xi given little y, right?
Yes, sir. Yeah.
But if y is some crazy random variable, in general, it could be, I mean, it may not have too many applications, but it could be some mixture of some Cantor random variable, something like that could be there, right? Then it's not, you cannot define it like this. See what
Okay.
I mean? That's why you go to sigma algebra definition. So in that definition, so expectation of x given y should be understood as is basically just expectation of x given sigma algebra generated by y.
Yes, sir.
Like that. Okay. Likewise, expectation of x given a is just expectation of x given the sigma algebra null null a complement omega.
Yeah.
Right, this will just be expectation of
Yeah. The course
given the sigma algebra null
by
omega
event A.
a complement.
Yes, sir.
That's all. Okay, that's so everything can be understood. So it's just a unifying theory of conditional expectation.
Okay. So here just we can't calculate, we just verify. We assume that this will be the expectation and then we verify these conditions. And if it satisfies these three, we say that this
It is a conditional expectation. Yeah.
So it's like,
Geometrically, it's the projection, right? F. So if you look at some, so this may not be the original. So this could be some G, right?
yeah, G
So G is some subsigma algebra of F.
Yes.
Right? So you're projecting X. So if X is some random variable, you're projecting X into the subspace of G measurable random variables. It's like a foot of the perpendicular.
Okay.
Okay.
It's hard to imagine.
Yeah, it's a little hard to imagine, but let me just draw this picture, right? So it's based, see, this picture is a space of two, finite, let's say the space of finite variance random variables, okay? And let's say G, this is some subspace G, okay? This is some subspace of G measurable random variables.
Yes.
Okay. Then expect, so this is X, okay? And you're looking at among the G measurable random variables, what is the one that is closest to X? That is expectation of X given G, this guy.
Okay.
Okay. So what is the best G measurable approximation of X is the question.
Okay.
Okay.
Yes, sir.
So it's like you think of it as Euclid. It's not actually a Euclidean space. It's an infinite dimensional Hilbert space. I think I mentioned this. In that space, you can project random variable X onto the some subsigma algebra G, right? And that's what this is.
Okay.
But
yes, sir.
if you don't get this, it's okay.
Yeah.
For the purpose of applications, this is okay.
Yeah, when we write this conditional distribution fxy, we write like the conditional distribution of like the conditional distribution is equal to joint distribution divided by the marginal of particular the one which we are having in the condition.
Yeah.
So from there to the like in the continuous case, how we go to the density the density formula. We have in the distribution we have that expression, and then we go to density, and also we get the same type of formula.
Yeah. So if you have let's say let x, y be jointly continuous, right?
Yes, sir.
So with density fxy of xy, right?
Yes, sir.
So I'm defining f x given y equal to y, right, has
Yes, sir.
probability that x less than or equal to x given y lies in y comma y plus delta, where limit delta going to 0, right? Is that the one you're talking about?
Sir, we have like fx. If I write this in density also, if I want a density of x, like random variable x, then I will have this joint density divided by the joint density of y. And same goes with the when we have distribution. If I want a distribution of x, random variable x, then we will have the joint distribution divided by the marginal distribution or the distribution of other random variable which have been in
It's
the
not
condition.
true. So what is true is that from this derivation, if you see my lecture, this is what comes out. Okay. Whenever fy of y is non-zero.
Yes, sir.
This
Yes,
is all
sir.
you get. If you want to
This
get
is
big fx
yes.
of x given y equal to y, you have to integrate this function over x.
Okay, so this is the definition, and then in the distribution we go from here.
Yeah, for distribution, you have to, this is a density. This is the definition of conditional density. Conditional PDF, probability density function. You integrate this over x, you will get conditional CDF.
Yes. So then we will get the almost same formula.
Yeah.
It will replace by distribution.
Yeah. So I want to say this fx of x given y equal to y is simply the integral of little fx given y. Sorry. Fx big x given big y of x given y dx. You want to call this du or something.
Yes.
U is equal to minus infinity to x.
X.
Okay.
Yes, sir.
Little y is fixed. That's the point.
Okay, then we'll integrate it and it will become.
That's all. Okay. So you take, when they're jointly continuous, you take the joint density divided by marginal density.
Okay.
Since you are dividing by marginal density, you need that.
Yes. In case of that what event space thing, we don't put these things, na. These problems doesn't come there, na. The expectation, conditional expectation when we were discussing.
Yeah, see, even in the jointly continuous space, jointly continuous world, you can define conditional expectation as an expectation over this conditional density, and then take the random variable version of it.
Yeah, you just told that.
You can do that. So in the discrete world, there is no problem. In the jointly continuous world, there is no problem.
Okay.
In all other cases, there will be a problem.
Yes, sir.
That is all. Okay.
Yes, sir. Somebody asked something.
Is it legal to use library Genesis to download Grimmett-Sturzaker? Probably not.
Sir, can I ask one question aside from the topics which we're discussing in class?
Okay.
Basic about random process. Like when we are doing defining random distribution for random process, instead of defining it for all those uncountable, like all for all t, we make it finite, and then we have the finite distribution, and we all everything, whatever calculation and whichever thing we do with in this random process, we do this with this finite distribution.
So you're taking a process x of t?
Yeah, like when process x of t, and because t is like this t belongs to R or something like that, where it is we can't do, like it's not countable, so, or finite.
No, you can do it. It's just that it's a little more advanced.
Okay.
Right? So each little omega corresponds to a function now.
Yes, yes,
function of time, right?
yes.
So each elementary outcome is a function or corresponds to a function of time.
Yes.
So your sample space is a space of all functions or something like that.
So it will become uncountable.
Yeah, it's uncountable. So you have to put a Borel sigma algebra on those for, it's more complicated.
So for uncountable, we don't have those things that we will do there some, or like union, and then we will uncountable unions and all those concepts will be not there, no?
Yeah. So
How will we say that they are in sigma algebra when we will have these
it's a little
evaluations?
more complicated, right? Now in the space of functions, you have to define Borel sigma algebra on the space. So for example, on the space of continuous functions, you can do that.
Okay, so for these things, I have to go to measure.
Yeah, you have to do. You have to look at the space of functions and what topology, or it gets a lot more complicated. To do this rigorously gets a lot more complicated.
Okay, then I'll do next semester.
Yeah, so the serious stochastic processes course in the math department will do all this.
Yeah, I met you.
Brownian motion, for example, Brownian motion, which is very commonly studied, it has sample paths that are continuous, almost surely continuous. So basically, each Brownian motion sample path is a continuous function, and continuous functions have the same cardinality as reals.
Yes.
The set of all continuous functions from R to R.
They are uncountable.
They're uncountable, but they have the same cardinality as reals.
Okay.
So just like reals have a Borel sigma algebra on them, the space of continuous functions have a Borel sigma algebra on them. Okay. So the probability measure, the Brownian motion inducer corresponds to a probability measure on it's basically on the Borel sets of continuous functions from R to R. Okay. So it gets a little more complicated.
Yes, sir. I have met you during SPCom.
Huh?
I met you during SPCom in ISC when you came this year.
I see.
We had a photo together. So I am taking this course by Parimal here.
Okay.
He's teaching this random process. So next semester, maybe I will take measure theoretic.
Oh, so you're a student, a PhD student in ISC.
Yeah, I am PhD student here.
Okay, you should definitely take measure theory.
Yeah, that's what I'm asking. Like, is these questions should be learned right now, or it has to take more concepts and more understanding to go through these things? Because right now,
what is in this course is a minimum for you.
Yeah. I have other topics also. He added data process, Markov chains, Markov process, and also Poisson process. Everything is there.
Those things I have recorded in the other course.
Yeah. So okay. So which book you suggest for this random process things to study? Like Grimmett and all is not covering the
Ross, I think to start, for the engineering students, I think Ross is a good book. Stochastic Processes by Ross.
Okay, sir. I will go through that.
Gallagher's book is what I learned from. It's more applied. It's not doesn't get too mathy, and therefore it's good for learning first time.
Yes, sir. And for these this convergence thing, like because the concepts are very rigorous one, and when the problem comes, it's get very tricky to think and find those exception sets or the conditions where this distribution these things are happening, getting zero.
Yeah, you just have to know a few standard examples of counter examples and all that. Otherwise, you just apply for testing convergence, just apply the definition. Okay, don't do anything fancy. This is my general advice to everyone. Okay, just try applying the definition. If I ask you, does this sequence converge in distribution, convergence in probability, you just try to apply the definition.
Okay.
So
where is there any particular material where we can practice in these standard things?
There are many problems, right? There are many problems in Grimmett. If you look at chapter 7 or something, right? Where is convergence?
Okay, sir. I will. Yes, sir. Yes. The chapter 7 is there, convergence of random.
Yeah, that has many problems.
Yes, sir.
Anybody else with any other questions?
Somebody has asked question in chat. I think. One.
So that's some non-technical question. I think is correct. Is it correct to use relative grading in education? I'm not sure if it's correct. Yeah, I don't know.
And sir, like there was one problem I was not able to able to show. I wanted to ask when we are having mod of if x is a random variable, if I have the mod of x raised to the power n, then I'm able to show that this is a random variable because and it is also a convex thing. So I can apply all those inequalities, junction and all which we have. But if I have simply x raised to the power n, then is it a random variable? Because
See, all continuous functions are Borel measurable.
Yeah,
right?
but I'm not able to prove that x raised to the power n is a random Borel measurable or not. Because if it
every continuous function is Borel measurable, right? Pre-image of open sets are open sets.
Yeah, but when I'm writing it in a way like we normally do mapping and then showing.
No. You just look at for any function, continuous function, pre-images of open sets are open sets.
Yeah.
So that's enough to show that continuous functions are Borel.
Okay, so we can write that.
Continuous can be shown to be Borel.
Okay.
Right.
Now, normally when for x square or something smaller, we show like by doing calculation.
Yeah, that you can explicitly show. But for any continuous f, of which f of xn is x to the n is a particular example. Right? You know from real analysis that
yeah, I'm taking that course.
Images of open sets under continuous functions are open, right?
Yeah.
All that you need. And pre-images of closed sets are closed, right? And so open intervals will map to open sets, and the Borel sigma algebra is generated by open sets. That's all.
And if n is greater than 1, then it is convex, and we can apply our.
No convexity. Only
for Jensen and all we want to apply.
Jensen is different.
No, I wanted to check if I have x raised to the power n or something. Then in that case, if first I have to check if it is random variable or not. If it is random variable, then I have to check if it is convex or not. If it is convex, then only I can apply the Jensen.
Correct. So convexity is separate, but see any function of a random. So any Borel function of a random variable is another random variable.
Yeah.
Correct. Yes. And continuous functions are very trivially Borel functions.
Okay, I will try to prove that in normal sense.
Yeah. Okay.
Thank you.
Anybody else? We have a couple of more minutes.
Hello, sir.
Yes.
This is Bala Santosh.
Yes.
Sir, relative grading uses probability theory for education, right? Is it correct? I mean, we are modeling the students' marks as a random distribution. Is that correct?
No, I mean, yeah. See, if you ask me that, see, I don't think this is a moral issue, right? So I don't think that you should grade students as being, especially in graduate level, right? Are you better than others should not be a consideration. I feel it should be about have you learned what you are meant to learn.
Okay.
Right. But then sometimes this absolute grading becomes very tough on students in the sense that suppose the exams become hard or easy or whatever. What if everybody gets below 70? Right? Can you start your grading at C or something or D or something?
So you could reduce the pass mark, right?
Yeah, we will always do that, which is what relative grading does. So relative grading, to the way I see relative grading, is not that you are making students compete against each other. The way I see it, it is more like how is the distribution, post facto distribution. So it's a data dependent distribution of the grade cutoffs. Rather than relative grading, you can think of it as data dependent cutoff assignment. That's all I would say.
Okay.
Instead of data, so think of it as data independent grading versus data dependent grading.
Okay.
Don't call it relative or absolute.
Okay.
Data independent means 90 means S, 90, 80 means A, or whatever, right?
Because the online BS degree program of IIT Madras uses absolute grading.
Yeah. So there they have decided that this is too complicated, right? This data dependent stuff is too complicated, especially since we are, when you have 400, 500 students, you are not going to see any separation of grades.
Okay.
Every 0.25 marks, there will be a person.
Okay.
So there will be no place to put a grade boundary at all, right?
Okay.
So even in large classes with 400, 500 students in IIT, sometimes we have to put cutoffs at 90, 80, 70, the usual way.
Okay.
There, the argument is that if you manage to get 90 or 80, you get the corresponding grade. Sometimes you may fall 0.25 marks short of the cutoff, but that's the way life is, right?
Thank you, sir.
Okay, good. Thank you very much.
Thank you, sir.
Wish you all the best for the exams. Thank you.
Thank you,
Bye.
sir.